Again, it's my great pleasure to talk about this year's Nobel Prize, which goes to three brilliant physicists. In fact, this year was kind of strange because they had two different citations. One goes for the theoretical discovery of topological phase transition, and the other one goes for topological discovery of a phase of matter. So that's why, strangely, they gave half of that to David Thales and the other half to two people. I guess the reason is, even though the Nobel Prize Committee does not explain, is because Thales was in both of these two researches. Allow me to give you a couple of minutes of background on these three beautiful minds. David Thales, 82 years old, is an emeritus professor in Washington University, has been the recipient of several other awards, including the Wolf Prize, goes every year to an outstanding living scientist or an artist. Next is Duncan Halden. From a very young age, I guess his first paper was in mid-20 that he published, and it was well received. It's in Princeton University. And last but not least, Scottish brilliant scientist who works in the same area, and he is also collaborating. These three scientists have been working for the last 3 decades. This year's Nobel Prize was a very unexpected for the discovery they have done, which actually paved the road for future discovery of matters with exotic properties. Now, I need to take a couple of minutes and give a little bit of terminology lesson on a few definitions. One is topology. So topology is a branch of mathematics in which you associate characteristics of matters and geometries to integer values. This is called change stepwise. For example, electrical conductance is an analog, and you can change it as you want in any decimal. This is not a topological behavior. But if I, for example, show you a cinnamon bun, a donut, a German sesame bread, and a pretzel, so of course you might say, well, I kind of feel hungry, and some of them are salty, sweet, different recipes. These are the different characteristics of these four objects, but if you show these four to a topologist, the only thing she or he will say that these have only one topological invariant, and that is the number of the holes. So one has none, one has 1, 0, 2, and 3. And of course, we don't have 1.5 or 2 3/4 of a hole, and that is a very simple description of a topological behaviors. Next thing is superconductors. So superconductors are matters that in a normal temperature, they are very normal. They don't show any electromagnetic properties. But when you bring the temperature lower, and when I say low, I don't mean outside 8 degrees, I mean minus 185 degrees. So they become completely different. They get out of the closet and become superconductor. And this is the fundamental of, for example, maglev train, supersonic train that we have. And last but not least, I would like to talk about something called superfluids. So superfluids, unlike the one that we know, like a water, have 0 viscosities. And that means if you stir them, they would keep stirring indefinitely. So very strange. For example, liquid helium at 0 Kelvin, it is one of these fluids. And last but not least, allow me to give you a very simple chemistry lesson. So we know we have 3 phases. We have solid, gas, and liquid between. We have phase diagram, different temperature and pressure. You can add them, and you can change them. We have a 4th stage, which is called plasma, by the way. So plasma is the stage as a gas, but very different than normal gas. You bring the temperature very high, and you knock out electrons, and you create an ionic soup. So usually these are very, very conductive. But also we have a 5th stage. The 5th stage is where we really are interested. So this is called actually Bose-Einstein quantum condensate. So it's happening at almost 0 Kelvin, which is minus 273.3. You might say, what is wrong with you, scientists, that you always work in such a low temperature? Well, let me tell you something. I'm not a quantum physicist. My area is material science. But as much as I know, law of quantum mechanics are very hidden. So, Dr. Green said that, when you don't look, it's there. When you look, it's not there. So it's always mysterious. The only temperature at which you can see this law, it unveil itself and show its face, is at 0, which is 0 energy and 0 entropy. That's why there's lots of focus on actually try to understand matter at this temperature. So what happened was, in 1981, a brilliant professor, his name was Klaus van Kleitzing, a brilliant physicist, he got Nobel Prize in 1985. He did a mysterious experiment. He created a thin single layer of electrons at a very low temperature under enormous amount of magnetic field. And what he realized that this electrical conductance is not a linear. It goes 0, 1, 2, 3, and he try and try and try. Every single time was bang on, robust. They gave him a Nobel Prize for that, but they didn't know why. Now, well, they didn't know why, but they know why this is behaving that way. I give you a little bit metaphor. Scientists sometimes they find something. They go in a dark room and they touch something and say, wow, there's a flat surface, another one here. You can guess. But unless someone comes and theoretically explain it, do mathematical modeling, and verify the mathematical modeling, it's no value, or at least we have not turned the light on to see what is going on. And this first Nobel Prize goes to these two brilliant scientists who actually approach topological behavior of these and connected, wrote everything, and it was bang on. It was perfectly matches after 3 decades. So that's why the first citation was. The second one, and I quickly go over that, is again related to another experiment. So if you have a two-dimensional liquid, so we want to say what is two-dimensional? It means one atomic layer of a liquid. So mathematically it was proven that it's impossible this to participate in a phase transition. You know, if you have water and you freeze it, become ice, in a long range, this has a crystallographic structure. But when you have one atoms, how does it work? Mathematically, it was impossible. But often what something we call it impossible is because we have not discovered everything, or we have not considered all the possibilities. And that was the other, Thales and the other professor realized. Maybe there is something that they did not consider, and that was considering vortices. They realized that, yes, it is possible mathematically to prove it. So in a sense, in a very low temperature, 0, this single atom two-dimensional liquid has internal vortices, one clockwise, one counterclockwise. That's why I think about a kind of a small ship. It goes straight. It doesn't go left or right. The phase is stable. But as soon as you increase the temperature slightly, then these two become disconnected. And that's why the phase transformation happens. A very different phase transformation, but that is what exactly is. So in a truly beautiful work, I mean, I am in no position even to tell that, but it's completely revolutionized. The world is very excited about what they can accomplish with that. One of the main applications could be in what we call it quantum computing. So I guess I ended here with 8.5 minutes. That was 80 years of experiment in 8 minutes. Thank you.